For thousands of years, the night sky has been silent. We looked up and saw stars. We imagined gods, stories, constellations. But we never expected the sky to answer back. The universe, as far as we understood, was distant and indifferent. Light traveled to us from unimaginable distances, but it carried no voice, no intention, no signal meant specifically for us. That changed in the 20th century. Not because aliens landed, not because a spaceship appeared, but because we learned to listen. Radio astronomy began as an accident. In the 1930s, an engineer named Karl Jansky was trying to track down sources of radio interference for telephone communication. Instead of eliminating noise, he discovered something else entirely, a steady hiss coming from the center of our galaxy. The sky was not silent. It was whispering. From that moment on, humanity built larger and larger radio telescopes. Giant dishes pointed toward space. Arrays of antennas scanning invisible frequencies. We realized that stars, galaxies, and exotic objects emitted radio waves constantly. Space was not empty. It was full of signals. Most of them were natural, predictable, understandable once physics caught up. But not all of them. In 1967, a young graduate student named Jocelyn Bell Burnell was analyzing radio data when she noticed something strange. A repeating pulse. Extremely regular. Precise. Every 1.337 seconds, like a cosmic heartbeat. At first, the signal made no sense. It was too consistent to be random noise. Too precise to be a known stellar process, at least as far as scientists understood at the time. Half-jokingly, the team labeled it LGM-1. Little Green Men. For a brief moment, serious scientists considered the possibility that the signal could be artificial. That somewhere in space, an intelligent civilization was transmitting a beacon. The truth turned out to be something equally astonishing. The signal came from a pulsar, a rapidly rotating neutron star, spinning with incredible speed and emitting beams of radiation like a lighthouse. It was not aliens, but it was something humanity had never seen before. And it proved an important lesson. When we detect something unexplained, the universe usually has a stranger answer than we expected. Yet sometimes, the answer does not arrive. In August 1977, a radio telescope at Ohio State University detected a signal that remains one of the most famous mysteries in astronomy. It lasted 72 seconds. It was strong. Extremely strong. Strong enough that the astronomer reviewing the printout circled it in red ink and wrote one word beside it. Wow. The wow signal came from the direction of the constellation Sagittarius. It matched the frequency scientists believed an intelligent civilization might use to broadcast across interstellar distances, the hydrogen line, a natural universal frequency. And then it disappeared. It was never detected again. For decades, astronomers have searched the same region of space. Nothing. No repetition. No pattern. No confirmation. Theories range from comet reflections to unknown astrophysical phenomena. Some suggest it was terrestrial interference. Others insist it was something else entirely. But without repetition, science remains suspended in uncertainty. The wow signal exists as a single moment. A cosmic anomaly. A message without a sender. And it is not alone. In recent years, astronomers have detected phenomena called fast radio bursts, incredibly powerful pulses of energy that last only milliseconds. In that fraction of a second, they can release more energy than our sun produces in days. Some repeat. Some do not. Some come from distant galaxies billions of light-years away. Others appear closer. For years, scientists had no explanation. Were they neutron stars? Black holes? Collisions? Artificial signals? Gradually, evidence began to point toward highly magnetized neutron stars known as magnetars. But even now, not every fast radio burst fits neatly into that explanation. There are still signals that behave strangely. Signals that repeat in irregular cycles. signals that appear to flicker on and off without a clear mechanism. And then there are signals we may never fully understand because the source is gone. In 2003, a strange radio signal known as the Perseus flare puzzled astronomers. It seemed to originate from deep space. It was intense and brief. Years later, researchers realized something unexpected. The signal came from a microwave oven. Specifically, from someone opening the door of a microwave before the timer finished. It was not cosmic at all. This revelation embarrassed no one. Instead, it reinforced how careful science must be. The universe is mysterious, but sometimes the mystery is in our kitchen. Still, not every unexplained signal ends with such a simple answer. In 2019, astronomers detected a signal that repeated every 16 days with surprising precision. It would flare, fade, then return again in a predictable cycle. Natural. Possibly. Artificial. Unlikely, but the regularity invited speculation. The deeper we listen, the more complex the sky becomes. Space is not a silent void. It is a storm of electromagnetic noise. Pulsars ticking. Magnetars erupting. Black holes feeding. Galaxies colliding. And hidden among all of it are signals we do not yet understand. The question is not whether the universe speaks. The question is whether we are hearing it correctly. Because sometimes, the most unsettling possibility is not that we have detected aliens. It is that the universe itself is far stranger than we are prepared to accept. When astronomers search the sky, they are not looking for voices. They are looking for patterns. The universe produces enormous amounts of noise, random radiation, background interference, natural emissions from stars, gas clouds, quasars, and black holes. Most of it can be described by physics. Most of it follows rules. The challenge is simple in theory and overwhelming in practice. Find the signal that does not follow the rules. After the discovery of pulsars and the mystery of the wow signal, scientists realized something important. The universe is capable of producing events that look artificial until we understand them. So every new anomaly must pass through a filter of skepticism. In the early 2000s, astronomers began detecting strange bursts of radio energy in archived data. They were short, sometimes only a few milliseconds long. They were intense, far more powerful than typical background noise. And they appeared to come from deep space. At first, many researchers dismissed them as interference. Equipment glitches. Satellite reflections. Human technology leaking into observations. But the signals kept appearing. They were eventually named fast radio bursts, or FRBs. The first confirmed FRB was discovered in 2007 in data that had been sitting unnoticed for years. It had traveled across billions of light-years. Its energy release, compressed into milliseconds, was extraordinary. And no one knew what caused it. Unlike the wow signal, FRBs were not a single isolated event. More were found. Then more. Some repeated. Others appeared only once and vanished forever. The repeating ones were especially puzzling. If a signal repeats, it suggests a mechanism. Something rotating. Something orbiting. Something cyclical. But the patterns were inconsistent. One repeating FRB exhibited a 16-day cycle. It would emit bursts for several days, then fall silent, then return again. Another showed irregular flaring. Some repeated hundreds of times. Others never returned. At one point, speculation intensified. Could these be artificial? Could they be transmissions? Beacons? The problem was scale. The energy involved was immense. To produce a fast radio burst intentionally would require technology far beyond anything humanity possesses. Entire stars' worth of power concentrated into milliseconds. Gradually, evidence began pointing toward magnetars, neutron stars with magnetic fields trillions of times stronger than Earth's. These objects are among the most extreme environments in the universe. Their crusts crack. Their magnetic fields twist and snap. When they release energy, the effect can ripple across galaxies. In 2020, astronomers observed a fast radio burst originating from a magnetar within our own galaxy. It strengthened the case that at least some FRBs are natural. But not all of them behave identically. Some remain statistically strange. There are bursts whose polarization patterns shift in unexpected ways. Signals that scatter through space in patterns not fully explained by known plasma distributions. Variations in frequency drift that resemble sliding tones. Every time a new anomaly appears, excitement rises. Not because scientists expect aliens, but because anomalies are where discovery lives. Yet not every unexplained signal originates from distant galaxies. Sometimes, the mystery is closer. In the 1990s and early 2000s, radio astronomers repeatedly detected strange bursts that appeared cosmic. They came from random directions. They were brief. They were powerful enough to raise questions. Eventually, someone noticed something unusual. The bursts happened around lunchtime. After years of confusion, researchers traced the source. When staff in the observatory kitchen opened the microwave oven before the timer finished, it emitted a short burst of radio noise that escaped the shielding and was detected by sensitive instruments. The signals were named peritons. They were not from deep space. They were from reheated food. The lesson was humbling. Before declaring something cosmic, eliminate everything human. Still, even after accounting for microwaves, satellites, aircraft radar, and atmospheric interference, genuine mysteries remain. There are signals known as long-delayed echoes, reports dating back to the early days of radio experimentation. Operators claimed that sometimes their transmissions would return seconds later, delayed far longer than expected from atmospheric reflection. Some speculated that the echoes were bouncing off distant plasma clouds. Others suggested far stranger possibilities, including artificial reflectors or unknown structures in space. Most modern scientists attribute these reports to ionospheric anomalies or observational errors. But the phenomenon was never fully reproduced under controlled conditions. It remains one of those historical curiosities that lingers on the edge of explanation. Then there are cosmic signals that are not bursts, but absences. In 2012, astronomers using the Hubble Space Telescope observed a faint galaxy that appeared to lack dark matter, the invisible substance believed to hold galaxies together. If confirmed, it would challenge decades of cosmology. Later observations questioned the initial measurements. The debate continues. Was the signal misunderstood? Were the distances miscalculated? Or did we glimpse something that does not fit our models? Sometimes the unexplained is not a sound. It is a contradiction. And then there is the most persistent signal of all. The cosmic microwave background. Discovered accidentally in 1965, it is the afterglow of the Big Bang, radiation filling the universe uniformly. It is not mysterious in origin. But within it are tiny fluctuations, temperature differences measured in millionths of a degree. These fluctuations map the structure of the early universe. But some anomalies remain. There are cold spots larger than expected. Asymmetries between hemispheres. Statistical oddities that may be random, or may hint at physics beyond our understanding. Cosmologists debate whether these are meaningful patterns or simply the human tendency to find structure in noise. This tension defines much of astronomy. The universe produces enormous amounts of randomness. Humans are pattern-seeking creatures. We evolved to detect signals in chaos. But sometimes the chaos is real. And sometimes the pattern is. The deeper we look, the more sensitive our instruments become. Radio telescopes now operate as vast arrays spanning kilometers. Projects like the Square Kilometre Array aim to monitor huge portions of the sky continuously. Artificial intelligence now scans data streams, searching for anomalies that human eyes might miss. This increases our chances of detection. It also increases the number of unexplained events. Because the more precisely we observe reality, the more complexity we uncover. Not all signals are messages. But not all noise is meaningless. The universe does not promise clarity. It offers data. And within that data are moments that do not yet make sense. Some will be explained in time. Pulsars were once mysterious. FRBs may eventually become routine. Strange polarization patterns may be mapped to specific astrophysical processes. But some signals may remain singular. A burst that happened once. A fluctuation that never repeated. A measurement that defies neat categorization. Science advances by reducing the unexplained. Yet it never eliminates it entirely. Because every time we solve one mystery, we uncover another layer beneath it. And somewhere, in the constant background hiss of the cosmos, there may still be signals we have not recognized for what they are. Not because they are hidden, but because we do not yet know how to listen. If the universe is full of noise, then how would we recognize a voice? This question has guided one of the most ambitious scientific efforts of the last century: the search for extraterrestrial intelligence. SETI is built on a simple assumption. If another civilization exists and has developed radio technology, it may emit signals that stand out from natural cosmic sources. Artificial transmissions, at least by our current understanding, would likely have characteristics that nature rarely produces. One of those characteristics is narrowband transmission. Most natural cosmic radio emissions are broadband. They spread across many frequencies at once. Artificial signals, by contrast, often concentrate energy into a very narrow slice of the spectrum. Human radio stations do this intentionally. It is efficient. It reduces interference. So SETI researchers search for narrowband signals. They scan millions of frequencies. They look for spikes, signals that rise sharply above background noise at a specific frequency. If such a spike drifts in a way consistent with planetary motion, it becomes interesting. But interesting does not mean artificial. Earth itself is loud. Satellites transmit constantly. Aircraft radar reflects signals unpredictably. Military communications, GPS signals, even poorly shielded electronics can contaminate data. Before any anomaly is taken seriously, it must survive layers of filtering. Over the decades, there have been moments of excitement. In 1977, alongside the WOW signal, several narrowband signals briefly raised eyebrows. None repeated. In the early 2000s, a candidate signal known as SHGB02+14A was detected in the direction of the constellation Pisces. It exhibited properties consistent with a narrowband transmission. It appeared multiple times over several years. It was never confirmed. Its origin remains unclear. In 2015, astronomers detected unusual light fluctuations from a distant star known as KIC 846-2852. The dimming pattern was irregular and dramatic. Some speculated about comet swarms. Others, more cautiously, suggested the possibility of large artificial structures. The idea of a megastructure orbiting a distant star captured public imagination. But follow-up studies pointed toward natural explanations involving dust. The pattern faded. The universe resumed its ambiguity. One of the greatest challenges in searching for artificial signals is defining what artificial actually means. Human transmissions are structured. They contain modulation, repetition, mathematical encoding. But another civilization might not use radio in the same way. They might use frequencies we have not prioritized. They might compress data in forms we cannot decode. They might transmit rarely or only briefly. There is also the possibility that we are searching in the wrong era. The window during which a civilization uses detectable radio transmissions may be short. Humanity has been radio loud for barely a century. As technology advances, our transmissions become quieter, more directed, more fiber-based. If other civilizations follow similar trajectories, the overlap of detectable radio emissions between two species may be narrow. This is known as the cosmic coincidence problem. Perhaps signals have passed us by in the past. Perhaps they will appear in the future. But at this moment, the sky remains statistically silent. And yet, silence itself is mysterious. The Milky Way contains billions of stars. Many host planets. Some reside in habitable zones where liquid water could exist. The probability that life has arisen elsewhere seems high. So where is everyone? This question is known as the Fermi paradox. If intelligent life is common, we might expect evidence, signals, probes, detectable engineering, something. But despite decades of listening, we have found nothing conclusive. Some suggest civilizations destroy themselves before reaching interstellar capability. Others propose that intelligent species are rare. Some argue that advanced civilizations become technologically subtle, no longer broadcasting obvious signals. There is also a more unsettling possibility. What if signals exist, but we do not recognize them? Human pattern recognition is both powerful and limited. We evolved to detect familiar structures, faces, symmetry, rhythm. But alien intelligence may not follow familiar patterns. What if a signal appears random to us, but encodes meaning beyond our current mathematical frameworks? SETI researchers have considered this problem carefully. They often focus on mathematical universals, prime numbers, simple geometric ratios. These are concepts believed to be independent of culture or biology. If a signal contained a repeating sequence of prime numbers, it would immediately suggest intelligence. But so far, no such pattern has been detected. There have been candidate signals that briefly generated headlines. In 2020, researchers analyzing data from the Parkes Radio Telescope in Australia identified a signal labeled BLC1. It appeared to come from the direction of Proxima Centauri, the closest star to our solar system. It was narrowband. It drifted in frequency in a way consistent with planetary motion. For months, speculation quietly grew. Further analysis eventually suggested a terrestrial origin, likely interference from Earth-based technology. The pattern dissolved. This pattern of excitement followed by explanation is common. It reflects not failure, but caution. Declaring the discovery of extraterrestrial intelligence would be the most profound announcement in human history. The burden of proof is enormous. Scientists require repetition, independent confirmation, elimination of every possible terrestrial explanation. Until then, every anomaly remains just that, an anomaly. But the search continues. Modern SETI initiatives use machine learning to analyze vast datasets. Billions of signals are processed automatically, looking for statistical outliers. Projects like Breakthrough Listen have expanded the search across wider frequency ranges and deeper into space. The instruments grow more sensitive each year, which raises an uncomfortable thought. If signals exist and we still do not detect them, what does that imply? Perhaps the universe is not teeming with radio civilizations. Perhaps intelligence is fragile. Or perhaps advanced civilizations communicate in ways we have not yet imagined, through neutrinos, gravitational waves, quantum channels. Our search is shaped by our technology, and our technology is shaped by our imagination. There is another possibility that scientists rarely emphasize publicly but quietly consider. What if an advanced civilization intentionally avoids detection? In human history, technologically superior cultures observing less advanced ones often chose not to interfere directly. Some theorists propose a cosmic zoo hypothesis, the idea that Earth is being observed but not contacted. There is no evidence for this. But the absence of evidence is not evidence of absence. The deeper truth is simpler. We are listening to a universe that is unimaginably vast. Signals weaken with distance. Noise accumulates. Time stretches across millions of years. Even if a civilization transmitted a message directly toward us, the probability of alignment is small. Space is not just large. It is staggeringly indifferent to synchronization. And yet, we continue to listen. Not because we expect certainty, but because even a single confirmed artificial signal would redefine our place in reality. Until that moment, we live in ambiguity. The sky is full of signals. Some are understood. Some are not. And somewhere in that ocean of noise may exist a pattern we have not yet learned how to see. After decades of listening, one fact remains undeniable. We have not confirmed a single artificial signal from space. The sky is not empty. It is full of radiation, bursts, pulses, flares, background noise. But none of it has proven to be a message. And so the mystery shifts. It is no longer only about unexplained signals. It is about unexplained silence. The Milky Way contains hundreds of billions of stars. Many of those stars are older than our Sun. Around them orbit planets, some rocky, some gaseous, some located in regions where temperatures allow liquid water to exist. Statistically, Earth should not be unique. Life appeared here relatively quickly after the planet cooled. Intelligence, though rare and fragile, emerged within a few billion years. Technology followed almost immediately after intelligence. From a cosmic perspective, the jump from stone tools to radio transmission happened in an instant. So why does the galaxy not appear loud? Why does it not shimmer with artificial transmissions? This question unsettled physicist Enrico Fermi in the mid-20th century. During a casual conversation about extraterrestrial life, he reportedly asked, "Where is everybody?" It was not a rhetorical question. If intelligent civilizations are common, and if even a small fraction develop advanced technology, then over millions of years they should spread, transmit, explore. Evidence should accumulate. And yet, the sky remains quiet. This is the Fermi paradox. There are many possible answers. One possibility is that life itself is rare. Perhaps the conditions required for life are extraordinarily specific. Perhaps Earth was fortunate in ways we do not yet understand. Another possibility is that simple life is common, but intelligent life is rare. Evolution does not guarantee complexity. For billions of years, life on Earth remained microscopic. Intelligence may be an accident, not an inevitability. A more unsettling possibility is that intelligent life frequently destroys itself. Technological civilizations gain power rapidly. Nuclear weapons, environmental disruption, artificial intelligence, biological engineering. The gap between capability and wisdom may be narrow. If most civilizations collapse shortly after developing advanced technology, their window of detectability would be brief. They would flare, and then go silent. This idea is sometimes referred to as the Great Filter. A barrier somewhere in the progression from simple life to interstellar civilization. We do not know where that filter lies. It may be behind us, meaning life and intelligence are incredibly rare achievements. Or it may be ahead of us. There is also a quieter possibility. Advanced civilizations may choose not to broadcast. Early radio transmissions from Earth were loud and omnidirectional. But modern communication increasingly uses fiber optics, tightly focused beams, encrypted channels. Our planet is becoming less detectable, not more. Perhaps truly advanced societies communicate in ways that do not leak into space. Or perhaps they communicate across distances using methods we have not yet discovered, gravitational waves, quantum entanglement, technologies that leave no obvious electromagnetic trace. There is another idea, more speculative but persistent. What if the universe is not silent, but we are too early? The galaxy is over 13 billion years old. Humanity has been technologically active for barely a century. Our listening efforts span only decades. That is a blink in cosmic time. We may simply not have listened long enough. Or we may not yet be looking in the right way. Every generation of instruments has revealed phenomena previously unknown. Pulsars were once unimaginable. Fast radio bursts were invisible before the right equipment existed. It is possible that what we currently interpret as noise contains structured signals beyond our present comprehension. The history of science is filled with moments when data seemed chaotic, until a new theory revealed hidden order. Perhaps the universe is structured in layers of complexity we have not yet learned to decode. And yet, there is something powerful about silence. Silence forces introspection. If we are alone, even temporarily alone, then the responsibility for meaning rests entirely on us. If intelligent life is rare, then every civilization matters immensely. If the galaxy is quiet because intelligence is fragile, then survival becomes the most profound achievement. The search for signals is not only about finding others. It is about understanding ourselves. When we point radio telescopes toward the sky, we are asking a question that transcends science. Are we unique? Are we temporary? Are we early? Or are we simply not listening correctly? Every unexplained signal reminds us that the universe is not fully understood. Every explained anomaly reminds us that patience and skepticism are essential. And every year of silence sharpens the paradox. But there is another perspective. Perhaps the absence of a confirmed artificial signal is not a failure. Perhaps it is an invitation. An invitation to endure, to explore, to become the civilization that survives long enough to be heard. Because if signals are rare, then the responsibility to send one may fall to us. Somewhere, billions of light years away, another species may be scanning the sky, detecting unexplained bursts, analyzing patterns, wondering whether they are alone. And perhaps, one day, a signal from Earth will appear in their data. A narrowband spike. A deliberate sequence. A pattern rising above the noise. Until then, we listen. We catalog anomalies. We debate explanations. We refine instruments. And we live in the tension between noise and meaning. The universe does not promise clarity. It offers signals. Some understood. Some not. And perhaps, somewhere within that vast ocean of radiation, there is still a message waiting to be recognized. Not because it is hidden, but because we are still learning how to hear.